Chapter 1, Section 7. Finding absolute value. The absolute value of 10 is equal to 10 because 10 is 10 units from 0 on the number line. The absolute value of negative 1/2 is 1/2 because negative 1/2 is 1/2 unit from 0 on the number line. Notice that whether we're taking the absolute value of a positive or a negative, we're going to get an absolute value that's positive because absolute value is distance and distance is never negative. The absolute value of 0 is equal to 0. 0 is 0 units from itself on the number line. In number 4, if the absolute value of x is equal to 4, then x can equal what? The solution to this equation we find is that x could equal positive 4 because the absolute value of 4 is 4, or x could also equal negative 4 because the absolute value of negative 4 is also 4. So we get two solutions to this absolute value equation. Let's solve another absolute value equation. In this one, what's inside absolute value, 6x minus 3, could equal positive 15, or 6x minus 3 could equal negative 15 because we could have positive 15 inside absolute value or we could have negative 15 inside absolute value here. Either way, the absolute value is going to be positive 15. So we solve two equations to get our solution. In the first one, we're going to add 3 to both sides to get 6x alone, and 15 plus 3 is 18. Now we'll divide both sides by 6 to get x alone. X is equal to 3. Or over here, adding 3 to both sides, 6x is equal to negative 12. And dividing both sides by 6, we find that x could equal negative 2. So we get two solutions to this absolute value equation. X could equal 3 or x could equal negative 2. Let's try number 3. Solve the absolute value of 4x plus 10 is equal to 6x. So again, 4x plus 10 could equal positive 6x, or 4x plus 10 could equal negative 6x. And then we'll solve both equations for x. I'm going to subtract 4x from both sides of this equation and get 10 alone on the left. 6x take away 4x is going to leave 2x on the right. And then I'll divide both sides by 2 to find that x equals 5. Or on the other side, again, I'll subtract 4x from both sides. Negative 6x minus 4x is a total of negative 10x. And then divide both sides by negative 10. X should equal negative 1. Okay, but now because this equation has a variable x outside of absolute value as well as inside of absolute value, I need to be sure to check for extraneous or false solutions. So I'm going to check 5 first by substituting 5 into this equation for x to see if I get a true statement. So on the left, we have 4 times 5, which is 20, plus 10. We have the absolute value of 30. And on the right, 6 times 5 is 30. And we know that the absolute value of 30 is 30. This is a true statement. So x equals 5 is a good solution. But now we also have to check negative 1. So we'll substitute negative 1 into our equation for x. And simplify. 4 times negative 1 is negative 4, and negative 4 plus 10 is 6. We have the absolute value of 6 on the left. On the right, we have 6 times negative 1, which is negative 6. Now, absolute value is always positive, so this is a false statement. The absolute value of positive 6 should be positive 6. So since this is false, negative 1 is a false solution, an extraneous solution, and we only have one solution to this absolute value equation. Let's solve an absolute value less than inequality. If we're looking for values that will satisfy this inequality, we know that we are going to have values inside absolute value here that are less than 21 but greater than negative 21. So we're looking for some center of the graph between two values. So when we set this up, we're going to write a compound inequality, an AND statement, because 4x minus 9 could be less than or equal to 21, and 4x minus 9 has to be greater than or equal to negative 21. Now we need to solve both simple inequalities to find our solution. So in this one, we'll add 9 to both sides to get 4x alone. So we get 30 on the right, and dividing both sides by positive 4, x is less than or equal to. We can simplify over here, get rid of a factor of 2 top and bottom. So x is less than or equal to 15 halves. And the other side of this compound inequality, add 9 to both sides, getting 4x alone again. 4x is greater than or equal to negative 12, and dividing both sides by positive 4, x is greater than or equal to negative 3. So this is our solution. Since it's an AND statement, remember, we can write it in shortcut form. X is greater than or equal to negative 3, and x is less than or equal to 15 halves. Okay, and we'll graph our solution. Since it's an infinite number of solutions and not just 1 or 2, we'll graph on the number line. So I'll put 0 in the middle. I'll go negative 4, negative 8, negative 12 to the left for labels, and I'll go 4, 8, 12 to the right. Okay, graphing our critical values, negative 3. I'll locate and label that. I'll graph the solid dot there because equals is part of the inequality. X is greater than negative 3, so I'm graphing to the right. But I have an endpoint over here of 15 halves, that's 7.5. So I'll locate 7.5 and label. And I'll graph a solid dot again since equals is part of the inequality, and x can be less than 15 halves. So I'm shading to the left. So there's the center of the graph that satisfies this absolute value less than inequality. Let's try a greater than. Let's try number 3. The absolute value of 3x minus 2 is greater than 18. If we're looking for values inside absolute value here that are greater than 18, now we're looking for values to the right of 18 or values to the left of negative 18. So we're looking for the ends of the graph to satisfy this inequality, and instead of writing an AND statement, we write an OR statement. 3x minus 2 is greater than 18, or 3x minus 2 is less than negative 18. So we do the same thing here. We reverse the order of the inequality, and we change the sign of the number on the right. Solving on the left here, adding 2 to both sides, we get 3x is greater than 20, and dividing both sides by positive 3, x is greater than 20/3. Or adding 2 to both sides, 3x is less than negative 16, and then dividing by that positive 3, x is less than negative 16/3. Okay, now remember, an OR statement cannot be written in shortcut form, so we'll graph right away again. Graph on the number line. Get our labels again. Negative 4, negative 8, and negative 12 to the left, and 4, 8, 12 to the right. Okay, critical values. X is greater than 20/3, that's 6 2/3. So I'll locate 6 2/3. Oops. And label, we'll approximate it there. Okay, empty dot, because X cannot equal 20/3, it's greater than, so I'm shading to the right. Okay, and now my other critical value, negative 16/3, that's negative 5 1/3. So I'll locate that and label. Empty dot, because equals is not part of the inequality. X is less than, so I'll shade to the left. These values are less than negative 16/3. So we have the ends of the graph that satisfy this absolute value greater than inequality. Okay, let's look at an application problem. A food manufacturer specifies that every family-sized box of cereal should have a net weight of 25 ounces with a tolerance of 1.2 ounces. Write and solve an absolute value inequality that describes the acceptable net weights for the cereal in a family-sized box. So our absolute value inequality might look like this. We'll use W as our weight, and if I subtract the weight that we want it to be, 25, from W, and take the absolute value of that difference, that has to be less than or equal to our tolerance of 1.2. This is our absolute value inequality, and now if we solve it, since it's less than, we're going to write an and statement. W minus 25 is less than or equal to 1.2, and W minus 25 is greater than or equal to negative 1.2. Okay, and solving both parts of this compound inequality, we'll add 25 to both sides to get W as less than or equal to 26.2. And on the right, adding 25 to both sides, we find W is greater than or equal to 23.8. And because it's an and statement, we can write it in shortcut form with W, our variable for weight in ounces, in the center, and W is greater than or equal to 23.8 and less than or equal to 26.2. So there's our range for the acceptable weights in ounces. Include in your notes of this video guided practice problems 2 through 12, even problems only, found on pages 53 and 55 of your textbook.